This lesson is more to give you a conceptual understanding of partial fraction decompositions. So in the previous lesson, I'd gone over linear factors, but those linear factors were distinct. So here we have two different cases, right? We could have something that indicates repeated linear factors, or we have nonlinear factors. So instead of going more towards problems here, I will do that later when I cover the entire pre-calculus review. But here, it's more about the conceptual understanding. So if we have something that's talking about repeated linear factors, for instance, let me give you an example. If we have something like 5x squared plus 20x plus 6, right? And we're dividing this by x cubed plus 2x squared plus x. So we have something like that, right? And this is the overall value that we want to decompose, right? Or we want to split this into multiple fractions. The first step again would be to, because the numerator doesn't really change, right? We don't really care about the numerator. We don't alter its value. However, the denominator value, you want to factor that out, right? You want to see if you can bring those into distinct linear factors, or whether the factors remain repeated, or whether you end up with nonlinear factors. And you can really see that if you factor the denominator out. So we don't want to change the numerator, right? All we're really doing is we are changing the denominator, and really we're factoring the denominator. So if we do this, right, just looking at the denominator, we see that there's an x, right? That's common. So x times x squared plus 2x plus 1. This is something you get when you factor the denominator. Now you can see this, right? And you can further write this as x times x plus 1 times x plus 1, right? Because you can split this into x plus 1 squared. And so this is what you have in the denominator. And again, in the numerator, just assume that you have, or obviously you have 5x squared plus 20x plus 6. So this is what we have now. Now the rule for repeated linear factors, right? Because in the previous lesson, it was more about you had two factors. For instance, you had x times x plus 1. You would do a over x plus b over x plus 1, where a and b are just variables. So here what the technique is that you have a over x plus b over x plus 1, and because you have repeated linear factors, you would do plus c divided by x plus 1 squared. And so that's really the area that's important to understand, because you may be given something like x times x plus 1 cubed. If you have that, then you would do a divided by x plus b divided by x plus 1 plus c divided by x plus 1 squared plus d divided by x plus 1 cubed. And really, when you're talking about repeated linear factors, whatever degree you have, you're really going all the way till that degree. So if that makes sense, because we have x plus 1 squared here, we're going all the way till x plus 1 squared, and we're adding those different variables a, b, c. So that's the idea. Now you have the three different fractions, right? And you want to set this equal to this value over here. And really, if you think about, so I'll just do the common denominator thing. So looking at this, what's the common denominator? We know we have x plus 1 squared here, and we have x plus 1, and we have x. So if we think about this, this is x times x plus 1 squared. And now we can have a, b, c, right? And we can multiply each variable by what we need to multiply each variable by. So that means that if we have x here underneath a, we would do a times x plus 1 squared. Similarly, we have b, we would do b times x plus 1. And similarly, we have c, we would do c times x, because again, it's that same concept of common denominator. And the fact that we have this now, we can set this equal to this over here, right? We could set this equal to 5x squared plus 20x, oops, that looks pretty bad, 20x plus 6, and all divided by x cubed plus 2x squared plus 6. So we have something like that, right? just taking this expression and putting that here. And really, if you think about it, x cubed plus 2x squared plus x is this thing over here, right? I had earlier factored it out, but this thing and this thing are really just equal. And if these are equal, and we know that the expressions are equal, then clearly the numerator this numerator here and this numerator here, and this numerator here, they must also be equal. And so to really find what a, b, c are, again, what you would really do is, for instance, you would say that x is equal to -1, you know, so that we really eliminate a and b, and then we can find c from there, and then using system of equations, you can further derive the values of a and b. And so that's the technique. You're really trying to make the denominators the same, and knowing that the expressions are equal, you can then find the variables by setting the numerators equal to one another. And so the thing with repeated linear factors, you're using the same process, the same technique. The only thing here that you must remember is that if you have something like, if you have repeated linear factors, you have to go to the highest degree. So here we had x plus 1 times x plus 1, so we went to x plus 1, and then we went to x plus 1 times x plus 1. So that's the thing with repeated linear factors. Now, the other thing we have here is nonlinear factors, and this is interesting because it doesn't always have to be linear. So nonlinear factors, and when I say nonlinear factors, so I could just give an example here again. So we can have 3x squared minus 2x plus 2 all divided by x minus 2 times x squared plus 1. Now looking at this, we know that this is definitely a distinct linear factor, right? And so there's no doubt that we can write this as a divided by x minus 2, right? However, when we have a factor that is not necessarily linear, right? In this case, it's quadratic, and we cannot factor it out, right? We can factor x squared plus 1. Then you're going to write bx plus c divided by x squared plus 1. And so what's really happening is that whenever you have linear factors, right, we're placing in a variable that is that is a degree less. And when I mean a degree less, for instance, you have x minus 2, right? Here we're putting just a constant. So if this is degree 1, this is technically degree 0, right? It's x to the power of 0, because that's essentially 1, and so you're just left with that one variable, because here the linear factor would mean x to the power of 1. However, when we have x to the power of 2 on the top, the conjugate, you could say, is really going to be the linear factor. Here, the one less than the linear factor is the constant. Here, one less than the quadratic, or which is really degree 2, one less than that would be a linear factor, which we can write as bx plus c. We're using the same process. However, we should make sure that whatever we have in the numerator, its degree is 1 less, right? So here, instead of just saying b, we would say bx plus c. However, you have to be careful here, because say you had x cubed plus 1, right? You may think that we could say something like bx squared plus cx plus d, and that would be right if it was something else. However, if you think about this, x cubed plus 1 can be factored. If you know the formula, that's just x, it's x plus 1 times x squared minus x plus 1. This is how you can further factor this expression. And so really you have a quadratic now, right? You have a quadratic, and so now over this you will write something like bx plus c, and this is another distinct linear factor, so you will be using some other variable in the numerator. However, so with x cubed plus 1, you understand that if you have a linear factor and then you have a quadratic factor, you will be putting something that's 1 degree less, right? So here it will be bx plus c, and here it would be any variable. So it's important that you factor out x cubed plus 1, and you want to make sure that you are able to factor that expression out. If you're not, if you have something like, I don't know, if you had something like x cubed plus 2, then possibly you can't factor that out. And if you can't factor it out, then you would be using this technique here. You would be saying it's bx squared, it's bx squared plus cx plus d, because again, that's one degree less than the denominator. And similarly here, because x squared minus x plus 1 cannot be factored, you will be using the bx plus c, or again, whichever variables you want to use. But again, just make sure that the one thing in the numerator is one less in terms of the degree than the denominator. So that's the main thing. But if you can, always factor it out and see if you can factor your expression into distinct linear factors. So this is a conceptual idea behind partial fraction decomposition. So thanks for watching.